We often find ourselves racing through life, absorbed in our daily concerns, without a second thought about the true pace at which existence unfolds. But when we step back and look at the broader picture, beyond Earth, we begin to see the astonishing reality. We are speeding through the cosmic expanse, heading into regions where no photon or elementary particle has ventured before. Into the infinite void. Our solar system, our galaxy, and indeed the entire universe not only traverse space but actively expand, creating new space as they move. Feeling overwhelmed? Take a deep breath and join us as we embark on an extraordinary journey. We're setting out to explore the edge of the universe, and perhaps even a bit further. For our loyal followers, this isn't the first time we've ventured beyond the familiar bounds of our solar system and galaxy to ponder. What is the structure of the cosmos? What lies at the very edge of the universe? Does the universe have a center or limits? Is our existence part of a simulation, or is it reality? Could we be one of many worlds in a multiverse? With each discovery, scientists find themselves facing even more profound questions. Is the universe truly infinite, or just unfathomably large? Since its dimensions, age, and mass cannot be definitively measured, the notion of an infinite cosmos was born. According to Friedman's theory, a finite universe must be in a state of expansion or contraction. Yet, if the universe is infinite, the ideas of expansion and contraction become paradoxical. The concept that the universe could have emerged from a singularity the size of a neutron, as suggested by the Big Bang theory, challenges the perception of its infinity. If time is viewed as a linear vector moving forward with no reversal, it implies that time did not exist before the Big Bang. Einstein's theory indicates that space and time are interdependent, suggesting a moment when space might not have existed at all, or perhaps it did. Or maybe we simply do not know. The idea of an expanding universe began to take shape in the early 20th century when astronomers studied the behavior and distribution of galaxies. In 1912, American astronomer Vesto Melvin Slipher made a pivotal discovery that set the stage for future breakthroughs. He measured the redshifts of various galaxies and noticed that most exhibited Doppler shifts toward longer wavelengths, indicating their motion away from Earth. Building upon Slipher's work, Belgian astronomer Georges Lemaitre proposed in 1927 that the universe was expanding. But even before this, a significant breakthrough in mathematics occurred in 1915. It wasn't just the publication of Einstein's general theory of relativity, a groundbreaking work that revolutionized our understanding of gravity, space, and the dynamics of the universe, that made waves in scientific thought. What truly marked a pivotal moment in mathematics was the proof of a lesser-known yet fundamental theorem by Emmy Noether, Noether's theorem. This theorem was the first to show that in any physical system governed by conservative forces, where the action of the system displays differentiable symmetry, each independent differentiable symmetry corresponds to a conservation law. Simply put, when a physical system exhibits a certain symmetry, there is a physical quantity associated with that system that remains conserved. For example, if a system maintains rotational symmetry, meaning its behavior is unchanged regardless of its orientation, then angular momentum is conserved. This principle applies broadly, from spherical objects to celestial systems like the Moon orbiting Earth and the Earth-Moon system orbiting the Sun. These systems conserve angular momentum because the physical laws driving their motion remain consistent irrespective of their orientation, highlighting the theorem's importance. In 1929, discussions about the expanding universe gained momentum when Edwin Hubble published his findings. He measured the distances to galaxies and their velocities relative to Earth and discovered that nearly all galaxies are receding from us, with more distant ones moving away faster. This pivotal observation supported results derived from the general theory of relativity, as Alexander Friedman and Georges Lemaitre had applied its equations to the cosmos and concluded that the universe under gravity could not be static. It must either expand or contract. The realization that the universe was expanding led to the formulation of the Big Bang theory, positing that all observed matter originated from a single, extremely dense and hot state. This expansion happened rapidly, yet it did not imply a specific center from which galaxies moved outward, leaving many mysteries to unravel. As previously mentioned, in the context of mathematics and symmetry, if a system exhibits symmetry with respect to spatial translations, linear momentum is conserved. What type of symmetry leads to energy conservation? This is known as time translation invariance. It means that the laws of physics governing the behavior of particles and fields remain unchanged when a system shifts forward or backward in time. This fundamental property underpins quantum laws that govern particles, quantum fields, and interactions, dictating particle-antiparticle creation and annihilation, and influencing gravitational experiments conducted on Earth, within the solar system, and across the Milky Way. As long as the laws of physics remain stable over time, energy conservation holds. This principle applies to the strong and weak nuclear forces, as well as electromagnetism. However, with gravity, this consistency only partially applies. The reason is that, unlike other physical forces that follow uniform rules regardless of time or place, gravitational interactions conserve energy only within a static, time-invariant spacetime structure, as described by Einstein's general theory of relativity. In scenarios involving a single-point mass, spacetime maintains its structure over time and follows an exact solution known as Schwarzschild space. In this context, the equations, coordinates, and laws remain time-invariant, ensuring energy conservation. However, in an expanding universe, this no longer holds true, complicating the notion of energy conservation for gravitational interactions. In our actual universe, the curvature of spacetime is shaped by the distribution of matter and energy. This curvature, in turn, governs the motion of matter and energy. The relationship is dynamic and reciprocal. The arrangement of matter and energy affects how spacetime evolves, and this evolving spacetime, in turn, influences the behavior and distribution of matter and energy within it. In a universe uniformly filled with matter and energy, as ours is on the largest cosmic scales, spacetime is not static like Schwarzschild spacetime. Instead, it is described by the Friedmann-Lemaitre-Robertson-Walker metric, named for the scientists who studied it. This type of spacetime must expand or contract over time. Static solutions are inherently unstable, similar to the fluctuating emotions of a teenager. According to prevailing theories, the universe began as an incredibly hot and dense singularity, marked by the Big Bang. In the first minuscule fraction of a second, the universe underwent rapid expansion, or inflation, growing at a pace that exceeded the speed of light. During this brief phase, the universe expanded by a factor of at least 90. Following this inflationary period, data from NASA shows that the universe continued to expand, but at a reduced rate. As space expanded, it cooled, enabling matter to form. Approximately 1 second after the Big Bang, the universe was filled with particles such as neutrons, protons, electrons, positrons, photons, and neutrinos. Around 380,000 years after the Big Bang, the cooling allowed atoms to form during the recombination era, resulting in a transparent, electrically neutral gas. This event marked the onset of a dark period in the universe, as stars and luminous objects had yet to emerge. About 400 million years later, the universe entered the reionization era, gradually transitioning out of the cosmic dark ages. Over 500 million years, gas clouds fragmented, forming the first stars and galaxies, whose intense ultraviolet light ionized most of the neutral hydrogen. Today, we know there is a clear relationship between a galaxy's distance and its speed of recession. For instance, a galaxy located 1 megaparsec away from Earth recedes at a speed of 70 kilometers per second. A galaxy twice that distance recedes at 140 kilometers per second. Presently, there are two main methods for determining the age of the universe, often represented by the Hubble constant. The discrepancy between these methods lies in whether they observe relatively nearby cosmic objects or those at extreme distances. Despite these approaches, scientists still obtain varying results, hinting at possible unknowns or unaccounted for phenomena in the universe. Although the expansion of the universe initially slowed due to the gravitational pull of matter clumping together, about 5 to 6 billion years after the Big Bang, an enigmatic force known as dark energy began accelerating this expansion, according to NASA. This acceleration persists today. One might wonder why the universe's behavior could not be simpler, but calculations indicate it cannot be otherwise. Will the universe contract? Modern physics and cosmology face two profound challenges. 85% of the universe's mass consists of unidentified matter, and most of its energy originates from an enigmatic source. Observations suggest that dark matter acts as the glue binding galaxies, while dark energy drives the universe's expansion. The presence of dark matter is essential. Without it, galaxies would not form, and life as we know it would not exist. However, the existence of dark energy poses a more unsettling implication. If it continues to dominate, the universe will expand indefinitely, potentially leading to a heat death. In this scenario, stars would burn out, no new stars would form as gas resources deplete, and the temperature of the universe would drop to levels incompatible with complex life. As space-time continues to stretch, matter would become increasingly sparse, resulting in a universe expanding endlessly, devoid of observers or life. While this scenario might seem unsettling, it was once considered the most straightforward explanation in physics. However, the mysteries of dark matter and dark energy have proven so challenging that they now appear almost insurmountable. Attempts to attribute dark matter to unknown particles have so far come up short, and no widely accepted alternative has emerged. This situation is so difficult that some physicists have proposed revising gravitational laws to eliminate the need for dark matter entirely. Dark energy has presented similar difficulties. Initially believed to be a cosmological constant that exerted a uniform outward force across space, observations from the Planck Space Telescope told a different story. According to Planck, the universe's expansion rate, inferred from cosmic microwave background variations, is 67.6 kilometers per second per megaparsec. In contrast, data from the Hubble Space Telescope, which observed nearby celestial objects, indicated an expansion rate of 74 kilometers per second per megaparsec. As Naked Science has reported, the dark matter problem is not entirely hopeless. Since the launch of the LIGO Observatory, an unexpectedly high number of mergers between stellar mass black holes have been detected. Such frequent mergers imply the presence of far more black holes than previously estimated. For years, researchers have searched for elusive dark matter particles, like WIMPs, only to conclude that they likely do not exist. Yet, discoveries made between 2016 and 2020 hinted that dark matter might not require a new particle after all. Instead, its nature could be different from what was once assumed. If so, our universe might be cyclical, a so-called phoenix universe that has experienced repeated cycles of expansion and contraction. Stellar mass black holes, formed from the remnants of stars, should be clustered rather than uniformly scattered across the cosmos, similar to how stars themselves are found in clusters. Dark matter, which accelerates the edges of galactic disks, is found in dark halos surrounding galaxies. This has led some scientists to theorize that black holes could form clusters within these halos. However, two major questions persist. What explains the sheer number of these black holes, and why does dark energy seem stronger in our galaxy's vicinity compared to regions billions of light-years away? A pivotal article by Gorkovy and Tiobashev, published in the Astrophysical Bulletin, advances the search for answers. The authors highlight that not all stars can become black holes. Only about 1 in 1,000, primarily the most massive stars, achieve this fate. Given the estimated 100 sextillion stars in the observable universe, only 100 quintillion would become black holes, a figure far lower than what would be needed to account for the black holes observed by LIGO as dark matter. This suggests an unexpected source is necessary. The researchers introduced the concept of a phoenix universe, in which our universe has already undergone numerous cycles of expansion and contraction, possibly more than hundreds. In each cycle, the universe begins by expanding, as it is now. It then slowly transitions into a phase of contraction. As contraction progresses, black holes move closer together. During the final stage, the universe's diameter shrinks from its current 100 billion light-years to just about 10 light-years. At such an extreme compression, the density and energy of the cosmic microwave background increase, raising the temperature from 3 Kelvin to an astonishing 10 billion Kelvin. At these temperatures, atoms composed of heavy elements break down under the bombardment of gamma photons, while black holes, immune to such destruction, remain intact. In this hyper-compressed state, only black holes and some neutron stars survive. The most intriguing aspect is what happens next. In this confined space of just a few light years, trillions of black holes gather in close quarters, drastically increasing the frequency of mergers. Data from LIGO shows that each black hole merger converts about 5% of their combined mass into gravitational waves, which, as Einstein demonstrated, do not carry mass. Consequently, a considerable amount of mass in this contracting universe is converted into gravitational waves. With repeated mergers, the number of black holes halves, and the total mass of the universe decreases by at least 5% each cycle. This process continues, gradually reducing the universe's mass with each cycle and potentially leading to significant decreases over time. It's crucial to understand that the universe's contraction results directly from the gravitational pull of the matter within it. If significant mass loss occurs due to the merging of black holes, the gravitational mass may diminish to a point where it can no longer sustain contraction. Imagine reducing the sun's mass gradually within the solar system. Eventually, it would become too light and the planets would drift away. While not a perfect analogy, since the universe lacks centrifugal force, the principle highlights an essential concept of gravitational balance. In the Phoenix universe model by Gorkovy and Thiel-Bashev, as the universe compresses to around 10 light-years in diameter, heavy atomic nuclei are destroyed by gamma photons, while black hole mergers convert much of the dark matter into massless gravitational waves. When this transformation reaches a certain threshold, the contraction halts, triggering rapid expansion, the new Big Bang, marking the start of another cosmic cycle. At this stage, heavy elements no longer exist. Over time, as the universe expands and cools, the temperature drops enough for atoms of light baryonic matter, such as hydrogen and helium, to form. The supermassive black holes that survived the prior cycle serve as gravitational centers around which these gases coalesce, eventually forming galaxies. Gorkovy and Thiel-Bashev refer to these as seed black holes, foundational to galaxy creation. The concept of galaxies forming around central massive black holes isn't new, supported by observations of ancient early universe objects, but their mechanism had been unclear until now. The theory suggests that the Big Bang results from some dark matter, black holes, turning into gravitational waves. Yet the significance of these waves extends beyond their creation. When gravitational waves interact with black holes, they are absorbed, increasing the mass of black holes, essentially the dark matter in our universe. As this mass grows, the expansion of space slows, eventually reversing into contraction. The process resembles a massive pendulum. Kinetic energy shifts to potential energy as the pendulum climbs until it peaks, slows, and descends. Similarly, as the universe expands, gravitational waves' energy is converted into mass, leading to eventual contraction. At the contraction's peak, black hole mergers release energy as gravitational waves, igniting another explosive expansion, the next Big Bang. Superstring theory, once popular, lost traction when it failed to produce verifiable predictions. Gorkovy and Thiel-Bashev argue that supporting evidence for their model already exists. Their calculations align with the number of stellar mass black holes needed to explain LIGO's observed merger rates. Although frequent mergers occur, the number of black holes grows with each cycle, suggesting they could be far more plentiful than in a single-cycle universe. The abundance of black holes aligns with a universe that has undergone repeated cycles, making sense of the impossibility of deriving 100 sextillion black holes from 100 sextillion stars alone. Moreover, their model's estimate of supermassive black holes from previous cycles corresponds to current observations, where there is approximately one supermassive black hole per large galaxy, around 100 billion in total. Earlier cosmological models struggled to explain the existence of billions of such massive black holes so early in the universe's history, but this cyclical model provides an explanation. Yet, matching existing data isn't enough. A robust model must make new, testable predictions. The study's authors suggest that searching for dark globular clusters of stellar mass black holes in galaxy halos could be such a prediction. They conclude that analyzing stellar movements in astrometric catalogs, such as Gaia data, might reveal these hidden clusters within the galaxy disk. The rationale here is straightforward. As dark globular clusters pass between Earth and a star in another galaxy, they may occasionally create a gravitational lensing effect. This occurrence, while rare, would stand out distinctly against the backdrop of the sky, making it easier to identify. A standout feature of this model is its prediction of an extraordinarily massive black hole somewhere in the universe, far surpassing any supermassive black holes discovered to date. This colossal black hole would be so vast that eventually it would absorb the entire universe, including Earth and all its inhabitants. However, this concept does not imply a doomsday scenario in the traditional sense. Falling into a black hole only results in spaghettification, a violent stretching and death, if the black hole is of relatively small stellar mass. In contrast, entering a supermassive black hole would not produce such an effect. Due to its immense size, the tidal forces acting on different parts of a body would be minimal, avoiding the spaghettification effect. Falling into such a massive black hole would likely be painless and might even go unnoticed by most, except for astronomers. They would observe the gradual fading of the redshift from distant galaxies, signaling the approach of the main black hole's boundary. Eventually, this redshift would shift to blue, indicating the universe's contraction as the expansion halts and reverses. While this process may span billions of years, it doesn't mean Earth's civilization would survive. The contraction of the universe, according to Gorkov's calculations, may take another 10 to 20 billion years until expansion ceases, with the contraction phase lasting an additional 20 to 39 billion years. The end is inevitable. Initially, the night sky would become intensely hot, making life on all planetary surfaces unsustainable. Eventually, as the universe continues to shrink, temperatures could soar to 100 billion degrees, and gamma rays from relic radiation would obliterate all atoms. Survival through this contraction phase of the Phoenix universe seems unlikely. Whether there is any escape remains unknown. This groundbreaking article suggests a bold shift in cosmology, proposing one of the first comprehensive and logical explanations of dark matter and dark energy. According to this theory, dark matter is composed of relic black holes, while dark energy does not actually exist. The supposed repelling force of dark energy is instead attributed to the influence of the main black hole. This concept also explains why the universe's expansion rate is slower at distant points compared to the nearby universe. If the universe's expansion is a consequence of mass loss over time, the rate would indeed differ between the distant past and the present. The concept of dark energy demands a consistent expansion rate, but in this new model, the absence of dark energy nullifies this need. Another strong point of this theory is its explanation of a fundamental mystery in galaxy formation. For a long time, scientists have noted that galaxies could not have formed without the presence of supermassive black holes at their cores. Observations reveal these massive black holes already existing within the universe's first few 100 million years, some weighing billions of solar masses. This new model naturally explains their origin. Like the stellar mass black holes that form dark matter, they were inherited from previous universes that preceded our own Big Bang. This also implies that the earliest universe likely lacked a significant number of galaxies, as it did not yet have the seeds, massive black holes, to pull gas together and form galaxies. Transitioning from the strengths of the new theory, we must also consider its potential weaknesses. It is unlikely, to put it gently, that the work by Gorkov and Tyulbashev will be rapidly or widely embraced by the scientific community. The theory deviates too significantly from the established one-time universe model. While the notion of the universe undergoing numerous cycles of expansion and contraction isn't entirely new, even George Gamow, who predicted cosmic background radiation, entertained such a concept. The mechanisms introduced by Gorkov and Tyulbashev are distinctly unconventional. They propose that the universe contracts as black holes gain mass and expands when black holes release mass through gravitational waves. This marks an unprecedented shift in cosmology, so novel that it falls outside the consideration of most physicists. critics of the theory may find it so unfamiliar that they overlook Einstein's well-documented assertion that gravitational waves possess no mass. Detractors claim that the total mass in the universe cannot diminish, arguing that when black holes emit gravitational waves, this mass merely transitions, not diminishes, from one form to another. Another potential challenge is that accepting this model could lead to the abandonment of entire areas of research, including the hunt for WIMPs, dark energy, and certain quantum gravity theories. Historically, proponents of mainstream scientific paradigms have been reluctant to acknowledge when their theories become outdated, so it's improbable that this theory will be received differently. Dark matter and dark energy are currently focal points in modern astrophysics. The mystery surrounding dark matter has been recognized for quite some time. In 1884, Lord Kelvin noted that stars in the outer regions of the Milky Way's disk were orbiting the galactic center at far greater speeds than theoretical calculations suggested. To reconcile this discrepancy, it was necessary to hypothesize the existence of vast unseen mass beyond the visible disk, in the dark outskirts of the galaxy where no stars are present. Although Kelvin did not name this phenomenon, it was the French mathematician Henri Poincaré who in 1906 described Kelvin's observations and coined the term dark matter. Despite more than a century of investigation, our understanding of dark matter has seen limited progress. While we have gathered extensive data on other galaxies, these observations consistently reveal the same pattern. Massive, invisible forces influence the motion of stars on the outskirts. The term enormous is appropriate, as current estimates suggest dark matter constitutes about 26.5% of the universe's total mass, compared to just 5% for ordinary matter, the material that makes up stars, planets, and all known life. Yet, the precise nature of this vast unseen matter remains a mystery. Up until the mid-2010s, weakly interacting massive particles were the leading hypothesis for explaining dark matter. This theory suggested that dark matter particles interact minimally with regular matter, primarily through gravitational forces. However, various analyses, including those by Russian scientists, indicated that even if WIMPs exhibited weak non-gravitational interactions, their abundance would be such that they would pass through a human body at least once a day, potentially much more frequently. Theoretically, under certain conditions, WIMPs could damage human cellular DNA and potentially lead to cancer. Fortunately, extensive experiments conducted on Earth have found no trace of WIMPs. Physicists now agree that no known particle possesses a cross-section small enough to align with such behavior. Astrophysicist Ethan Siegel elaborates on the issue, stating that even if particles with these properties could exist, there would not be enough of them to account for the entirety of dark matter. Despite these setbacks, proponents of the WIMP theory remain persistent. Siegel wryly remarks, "Theorists can always adjust their models, and they've done this time and again, lowering the expected WIMP cross-section after every experimental null result. This is the poorest form of science. The only motivation here is to uphold an idea that actual data dismisses." Although research into WIMPs continues globally, using costly detectors, it now resembles a futile search, like someone hunting for lost keys under a street lamp, simply because it's the only spot with light. The most likely result of ongoing WIMP research is further years of inconclusive experiments, with no discoveries. Hopefully, however, some valuable insights will emerge during this pursuit. This brings us to a fundamental question. If WIMPs don't exist, could dark matter be composed of other types of particles that might be equally or even more dangerous? Or could it be something entirely different? Enter the MACO theory. MACO stands for Massive Compact Halo Object. In a galaxy, the halo is a spherical cloud of matter extending far beyond the visible disk, encompassing areas above and below it as well. Unlike WIMPs, MACOs aren't theoretical particles, but instead represent dense, dark objects. The main candidates in this category are black holes and neutron stars. Until recently, there were three key reasons why MACOs were not considered sufficient to explain most dark matter. The first reason involved the frequency of gravitational lensing observed in astronomical studies. Black holes, being highly dense and massive, create a gravitational lens effect when they pass between Earth-based telescopes and distant stars, amplifying the star's light significantly before gradually fading as the black hole moves out of alignment. Observations show that the actual frequency of such lensing events limits the number of Makos present, suggesting that they cannot account for all the dark matter. The second reason concerns the amount of ordinary baryonic matter produced during the Big Bang. Both black holes and neutron stars are formed from baryonic matter, and calculations indicate that if the Big Bang had created enough of it to account for a third of the observable mass of the universe, the isotopic ratios observed in stars would be markedly different from what we currently see. Thirdly, black holes and neutron stars are the remnants of massive stars at the end of their life cycles. The challenge lies in the fact that stars massive enough to evolve into neutron stars or black holes are exceptionally rare, representing less than 1% of all stars. Estimates suggest that only 1 in 1,000 stars will ultimately collapse into a black hole. This poses a significant problem. Dark matter is estimated to be 5.3 times more prevalent than the visible matter in the universe. How could this be possible if Makos originate from such a tiny proportion of all luminous stars? Quite simply, there aren't enough suitable candidates to produce Makos in the quantities needed to account for the vast amounts of dark matter observed. Up until 2016, the prevailing belief among astronomers was that while Makos existed, their contribution to the total mass of dark matter was minimal. This assumption was bolstered by the expectation that WIMPs would eventually be detected, a discovery that, to this day, has not occurred. The situation took a dramatic turn in 2016, thanks to the groundbreaking observations by the American LIGO gravitational wave detector. Over several years of intermittent operation, LIGO detected dozens of gravitational wave signals with varying levels of statistical significance, including more than a dozen confirmed with high reliability. Most of these signals were the result of black hole mergers or collisions between black holes and neutron stars. The detected black holes had masses ranging from several solar masses to dozens. This discovery raised a significant question. How could there be so many black hole mergers, especially involving black holes with such unusual masses? Before LIGO's operations, black holes of tens of solar masses were thought to be extremely rare. This dilemma is compounded by the fact that astronomers have developed methods to observe mergers of ordinary stars, where material from one star transfers to another before culminating in an explosive outburst. These events are not common, and black hole mergers were expected to be even less frequent. Given that only 1 in 1,000 stars evolves into a black hole, and that a merger requires a black hole to find a suitable companion, the odds seemed astronomical. Black holes have an average diameter of roughly 100 kilometers, so how could they draw close enough in the vastness of space to merge? Moreover, the formation of a black hole follows a supernova explosion, a powerful event that typically propels the black hole out of its original stellar system at high speed. This makes it even more improbable that two black holes, each expelled from different supernovae, would encounter and merge in the vast expanse of interstellar space. How could such rare events occur frequently enough for LIGO to register multiple detections each year? Since 2016, some researchers have proposed that the black holes detected by LIGO might actually be Makos. This theory suggests that a new category of extremely dark compact objects could be the key to solving the dark matter mystery. However, two major challenges remain: the previously noted scarcity of observed gravitational lensing events and uncertainty regarding how such a vast number of black holes could have formed in the universe. In 2017, an unconventional idea emerged. Makos may not need to be uniformly distributed throughout the galactic periphery. The stars believed to give rise to these black holes often form globular clusters at the edges of galaxies. These clusters are dense formations, containing anywhere from tens of thousands to 1 million stars, packed at distances averaging half a light year apart. In these regions, the night sky would be 100 times brighter than in our solar neighborhood. If black holes were to form similar dense, dark globular clusters, comprising a few thousand black holes each, the number of detectable gravitational lensing events would remain low. While each cluster could act as a significant gravitational lens, the chances of one aligning between Earth and a distant star would be minimal. The concept of dark globular clusters is particularly compelling because it could also explain the frequent black hole mergers detected by LIGO. The odds of two black holes approaching each other by chance are low, but within dense dark clusters, eventual collisions become far more likely. By 2019, another research team found that the mass of a galaxy's halo, estimated from the gravitational effect of dark matter, correlated closely with the number of visible globular clusters. Multiplying the number of these clusters by approximately 5 billion solar masses yielded a figure close to the total estimated mass of dark matter in a galaxy's halo. How do dark globular clusters fit into this? The answer is straightforward. Visible globular clusters typically do not exceed 1 million solar masses. However, there should be a significant relationship between the number of visible star clusters and unseen clusters of black holes and neutron stars. If these dark clusters form the majority of dark matter, they would exert the gravitational influence necessary to bind the visible clusters to their galaxy. This hypothesis is promising because it explains dark matter without introducing new particles. It is also verifiable with current astronomical techniques. Dark clusters would cause localized star disturbances at the edges of galactic disks as they pass by, leaving observable trails. This concept suggests that clusters of black holes and neutron stars could provide a more convincing explanation for dark matter than WIMPs or other theories involving unknown, elusive particles. Yet, one major issue remains. In a study by gravitational physicist N. Gorkovy and similar research, estimates indicate that up to 200 billion black holes with masses of around 5 solar masses would be required in our Milky Way alone. Given that the Milky Way holds approximately 400 billion stars and only a fraction could evolve into black holes, this hypothesis would necessitate several hundred billion black holes, far more than expected from known stellar processes. The mysteries of our universe extend far beyond just our own galaxy. According to current Big Bang theories, there's no clear indication of how such a massive amount of ordinary matter could have accumulated to form so many stars, which would ultimately give rise to an enormous number of black holes. Where could they have come from? We've been grappling with this question too. Interestingly, we still don't know if ours is the first universe, or if space-time undergoes cycles of expansion, like what we see now, followed by contractions and new beginnings. Observations today don't definitively distinguish between these possibilities. What does all of this suggest? The question of whether machos might ultimately prove superior to WIMPs and other dark matter candidates could be answered in the next decade. The Gaia Space Telescope is well equipped to detect perturbations caused by dark globular clusters within fields of bright stars. But it's important to note, even if machos do emerge as the solution, this may not offer as much comfort as we'd hope. While it could explain the dark matter puzzle that's puzzled scientists since 1884, the implications are profound. Today, the Standard Model places the age of the universe at about 13.8 billion years. Its story seems straightforward, a progression from an unfathomable initial density at the Big Bang to today's intense expansion in all directions, creating a roughly spherical universe with a span up to 100 billion light-years. But if black holes indeed account for dark matter, this simple linear narrative becomes far more mysterious. It would imply that our space-time may have cycled through countless eras of expansion and contraction, meaning that any solitary black hole or neutron star beyond galactic disks could be trillions of years old, predating even the formation of atoms. This Phoenix universe scenario is far more complex and vast than anything modern cosmology has depicted so far. In trying to address challenging questions, machos might only present physicists with even greater ones, questions that could prove exceedingly hard to answer definitively. In the massive survey, researchers at the University of California analyzed nearby massive galaxies within 100 megaparsecs of Earth, and in doing so, they inadvertently measured the Hubble constant, or the rate of the universe's expansion. Their findings differed from earlier models, showing a speed roughly 9% higher than theoretical predictions. This figure aligned with results published 2 years prior by Johns Hopkins University. Guided by Professor Ma-Chun Pei, the California team examined 63 elliptical galaxies using both ground-based and space telescopes, measuring variations in brightness to calculate both the galaxies' distances and their recession velocities. Nobel laureate Adam Riess's team at Berkeley, which famously demonstrated in 2011 that the universe's expansion is accelerating, had observed a similar discrepancy while studying stars in the neighboring Large Magellanic Cloud with the Hubble Space Telescope. They too found a speed about 9% higher than theoretical models suggested. Their findings, published in astrophysical journal letters, brought further attention to the mystery. We've long known the universe is expanding, but why it's expanding faster than anticipated remains unknown. While calculations point to one rate, observations reveal a quicker pace. Conventional wisdom says that for every megaparsec of distance from Earth, a galaxy's recession speed should increase by 67 kilometers per second. Yet Rice's measurements show an increase of 73 kilometers per second, a difference of 9%. Observations hinting at accelerated expansion date back to 2016 and were reaffirmed in 2018 with data from the European Space Telescope, Gaia. Now, Berkeley's latest findings have further strengthened this conclusion, with 2 independent groups arriving at near-identical results. Ma-Chun Pei and her colleagues detailed their findings in the Astrophysical Journal, attributing the accelerating pace of galactic movement to either dark matter or dark energy. Although these phenomena are not well understood, scientists believe that the repulsive forces they exert far outweigh gravitational pull. Robert Caldwell of Dartmouth College, along with researchers from the California Institute of Technology, explored one possible fate of this spreading apart phenomenon. They proposed that the universe could eventually reach a big rip, where it would expand so extensively that all matter, down to its smallest components, would be torn apart. Fortunately, this catastrophic event is predicted to be far in the future, about 22 billion years from now. But given the current pace of acceleration, this end may be drawing closer, accelerating, in a cosmic twist of fate. If the Big Rip scenario unfolds, the sequence would be catastrophic. 60 million years before the final breakdown, the Milky Way would be torn apart. 3 months before the end, the planets of our solar system would scatter. In the last half hour, Earth would crumble to dust, and ultimately, even atomic nuclei would disintegrate, leaving no trace of matter as we know it. What might come after the Big Rip? Perhaps absolute nothingness. But there's a chance that dispersed matter could coalesce into an unimaginably dense point, a singularity, which might trigger a new Big Bang. Much like the one that created our universe 14 billion years ago, this event could lead to the birth of a new universe. In contrast, scientists working on the Gamma Project, who study radiation from stars and star clusters across different wavelengths, have projected a longer life for our universe. Surveying 220,000 galaxies, they found that these galaxies' radiation is gradually dimming. In 2015, Professor Simon Driver from the International Center for Radio Astronomy remarked that the universe is slowly darkening. This fading, they concluded, will eventually lead to a universe void of light, like a lamp running out of fuel. If we trust the Gamma team's research, the universe may not be eternal, but complete darkness is still a distant event. Based on current calculations, all stars will burn out in 100 trillion years. After another 1,016 years, any remaining star material will be consumed by black holes. Eventually, in about 1,099 years, even black holes will disappear. This, in cosmic terms, is as close to eternity as we can imagine. What was before the Big Bang, from which our video now starts, you can easily remember by simply rewinding a bit, even from what your morning or this week began with. Though it may be a bit more challenging for some here, we are so accustomed to everything having a beginning that subconsciously we assume it for everything. However, what about something so old, even ancient, that its beginning cannot be found so easily. We've all heard about the Big Bang, but what preceded that event remains a mystery and nothing more than hypotheses. Despite the fact that the Big Bang theory is one of the most popular ones today, understanding it is not so simple. Moreover, it is crucial to remember that it is primarily a hypothesis, and we must consider the inaccuracies that scientists still need to eliminate with new astronomical observations and research. However, physicists have enough independent cross-data that makes the Big Bang theory the main starting point of modern cosmology. Everything around us is a direct consequence of an event that happened 14 billion years ago. According to the theory, space, time, matter, and energy were all confined in a fiery ball called the Big Bang. It expanded, and from its cooling debris, galaxies formed, including our Milky Way, one among approximately 2 trillion. The idea that the universe emerged from nothing was so insane that scientists were skeptical for a long time. However, existing evidence was convincing enough. Galaxies are moving apart like cosmic fragments, and the heat of the Big Bang still surrounds us in the form of cooled cosmic microwave background radiation discovered by radio astronomers in 1965. Today, scientists assume that all processes after the Big Bang were driven by the gradual cooling and thinning of the universe. As we know, temperature is a measure of particle motion, and as the temperature dropped, particles slowed down. The slower the particles move, the easier it is for them to come together. As the universe cooled down, initially flying quarks could merge into protons and neutrons and other hadrons and leptons. Then, the particles that had been obtained, continuing to slow down, began to form the first nuclei of familiar atoms, and so on. However, precisely what the universe was like during the Big Bang cannot be said with certainty. We can only assert that it was incredibly dense, and this changed over time. Everything we observe around us was incredibly tightly packed into a very small space in the beginning. But how can it be both infinite and at the same time so small? When people read about the theory, they might imagine that the universe was first smaller than an atom, then the size of a football, and so it expanded over 14 billion years. However, this analogy assumes that space initially had boundaries and an edge, but nothing suggests that the universe was not infinite even at the time of the Big Bang. Before that, it was smaller, and the object that occupied a square meter of space has now expanded to billions of light years. But even at the very beginning, the universe had no boundaries. Here's how it's explained by Professor Uriam Rocknes, a theoretical physicist at the University of Oslo. The entire observable universe comes from a tiny region that can be called a point, but nearby regions also expanded, and so did the next ones. Some of these regions are now so far away that we cannot observe them. If we think of the Big Bang as an explosion, it might seem like it started from a specific point at the center. However, when it comes to the birth of the universe, almost all galaxies are moving away from Earth in all directions. Therefore, Earth was never and will never be the center of the universe. Any observer on any other planet will also see galaxies moving away from them. In other words, the universe is expanding everywhere simultaneously. According to the inflationary model, the universe shortly after its birth experienced a very short period of exponential expansion, doubling its linear dimensions many times over. Scientists believe that this process began around the time of the strong nuclear force separation. This expansion, popularly known as cosmic inflation, was extremely brief, lasting only about 30 seconds. However, it increased the size of the universe by at least 10 to the 30, a billion times, possibly even more. But what if we want to look even further back in time, before the Big Bang? The main answer comes down to the fact that before the Big Bang, there was nothing at all. It means that the universe originated from nothingness, which is impossible even to imagine. When and why such a thing could have happened remains beyond comprehension. However, scientists insist on their position. Among them is the renowned theoretical physicist Stephen Hawking from England, who says that they didn't just imagine that the universe came from nothing. They arrived at this conclusion through rigorous mathematical calculations in which no one has found any errors. At some point in this mysterious nothingness, there might not have been familiar forms of matter, but it was not entirely empty, and certain processes might have been occurring that could give rise to small explosions. Ultimately, the Big Bang happened. To find evidence of this hypothesis, researchers try to create something similar to nothingness. They build special chambers from which they remove particles of matter and lower the temperature, almost reaching the coldness of space. Surprisingly, the resulting nothingness turns out to be something that can be studied in various ways. Here, we can think of vacuum energy and zero-point energy, but that delves into quantum mechanics, which would require much more time to explain. Still, many people disagree with the idea that the universe originated from nothing. Opponents of this hypothesis answer the question of what was before the Big Bang in various ways. Even though we know that the universe existed before the Big Bang, there is still very little that we can say about the nature of this ancestor of our universe. However, it can be assumed that something in its history led to a Big Bang, giving rise to our universe. Of course, there are other opinions. Perhaps before the Big Bang, there existed a universe similar to ours, or maybe entirely different. It is also possible to speculate that before our universe, there were at least two other universes whose collision led to the Big Bang. One can even imagine that the universe exists eternally, and in its history, Big Bangs alternate with big collapses. Such explosions could occur if the expansion of the universe changed to contraction. Finally, it can be assumed, and many agree, that at the initial moment of our universe's history, an incredible event occurred. The newborn universe rapidly expanded and inflated to enormous proportions, giving rise to bubbles in which different universes grew one after another. This way, a large universe emerged, also known as the mega-universe or multiverse. If this is true, just as our galaxy is one of billions of galaxies known to us today, our universe is one of many completely unknown other universes. But the most interesting, in our opinion, is the conformal cyclic cosmological model, abbreviated as CCC. According to this theory, the life of the universe consists of epochs, and each epoch's exponential expansion ends with a Big Bang, becoming a precursor for the next epoch. What would happen if one squeezes the distant future in the mathematical model of the universe, representing infinity as a finite boundary? What if the singularity of the Big Bang is stretched to the same smooth, finite initial boundary? According to the model, the universe goes through infinite cycles, where in each preceding cycle, the time in the future tends towards infinity, which becomes the singularity of the next cycle. It is assumed that the masses of all particles in the universe constantly and steadily decrease to zero over time, thereby increasing the energy. Additionally, an interesting assumption is that supermassive black holes, which are now detected at the centers of many galaxies, are relics inherited from past universes into our own. Professor Penrose's theory is fascinating, and we highly recommend exploring it. The cyclic theory exists in several versions, just like the inflation theory, and according to Professor Paul Stanford, the differences between them are purely technical and only interesting to specialists. The general concept remains unchanged. First of all, in our theory, there is no moment of the world's beginning, no singularity. There are periodic phases of intense birth of matter and radiation, each of which, if desired, can be called a Big Bang. However, each of these phases signifies not the emergence of a new universe, but merely a transition from one cycle to another. Space and time exist before and after each of these cataclysms, so it is entirely reasonable to ask about the state of affairs 10 billion years before the last Big Bang, from which the history of the universe is counted. The second key difference is the nature and role of dark energy. The inflationary cosmology did not predict the transition from decelerating expansion of the universe to accelerating expansion. However, when astrophysicists observed distant supernova flashes, standard cosmology didn't know what to make of the paradoxical results. The hypothesis of dark energy was proposed to reconcile these observations with the theory. Our approach is more internally consistent since dark energy is present from the beginning, facilitating the alternation of cosmic cycles. Nevertheless, as both Paul and Steinhardt note, cyclic theory has its weaknesses, particularly in explaining the collision and balance of parallel branes, i.e., lower dimensional spaces, from M-theory strings that occur at the beginning of each cycle. Other aspects of cyclic theory are better developed, but there are still many uncertainties to resolve. In conclusion, let's recall the following. Because events preceding the Big Bang have no consequences for observations, they can be excluded from the theory, and we can consider that time began with the Big Bang, as Hawking asserted. However, scientists still harbor hope of learning what existed before the beginning of time. Perhaps it was something grand or very dense, something that transitioned to us from another universe. There are more questions than answers, and for now, humanity is in search, and maybe someone among you will be able to tell the world what happened before the Big Bang. Have you ever wondered how our planet, our sun, and our galaxy came to be? Until recently, the universe was considered eternal, and its existence didn't trouble scientists. Albert Einstein even assumed the universe's eternity in his hypotheses and adjusted the equations of the theory of relativity accordingly. However, with the acceptance of the concept of the Big Bang, everything changed. Experts show that we live in the expanding and cooling remnants of a cosmic lump of matter. But what caused this initial explosion, and what preceded it? Did anything precede it at all? These questions are undoubtedly within the scope of science, but every attempt to answer them faces seemingly insurmountable obstacles, the infamous singularity, an infinitely small and dense point in which the entire universe, all the physics of the world, constants, matter, space, and time were compressed. Then, or during this event, the Big Bang happened, and everything listed above came into being. Nowadays, physicists have discovered the cosmic microwave background and started contemplating the very beginning. It's all a bit tangled, isn't it? The question remains, what was the problem with the existence of the cosmic singularity? It is one of the most serious problems in physical cosmology. The issue is that any information we have about what happened after the singularity can't provide us with any insight into what happened before it. Even now, so-called new physics leads us to the realization that our knowledge of the universe is still in its very early stages. Thus, at this moment, we can only talk about what we are capable of seeing with our eyes or through mathematical models on paper. One of the most frequently asked questions is, where exactly did the Big Bang occur? If there was an explosion, there must have been an epicenter. However, the reality is that our universe has no center. It is more accurate to imagine that the Big Bang occurred simultaneously everywhere in all points of the universe. Today, scientists assume that all processes after the Big Bang were influenced by the gradual cooling and decreasing density of the universe. As we know, temperature is a measure of particle movement, and as the temperature dropped, particles slowed down. Slower moving particles made it easier for them to interact with one another. During the universe's cooling, individual flying quarks merged to form protons, neutrons, and other hadrons and leptons. Then, these particles, continuing to slow down, began to form the first nuclei of familiar atoms. This period of the formation of the first atoms in the universe is called primordial nucleosynthesis, which lasted about 20 minutes after the Big Bang. During this period, the entire universe was heated to the state that we observe today inside stars. In this period, hydrogen and helium nuclei primarily formed in a ratio of 3:1, and these proportions of hydrogen and helium remain the two most abundant elements in the universe to this day. After the first nucleosynthesis, new atomic nuclei were hardly formed anymore, and the universe still remained hot, with matter existing in a plasma state. Electrons flew independently from nuclei, making the universe opaque to light. Photons constantly collided with electrons and couldn't travel straight, as if they were trapped in a mirrored labyrinth. This is why, by the way, you cannot see them through a daylight lamp or through our sun, which are also made of plasma and are therefore non-transparent. The universe continued to cool, and after about 300,000 years after the Big Bang, the temperature dropped sufficiently for electrons to join atomic nuclei. As a result, the universe became transparent. This moment is called recombination. The photons that filled everything around were no longer obstructed by electrons and could travel straight, instantly in all directions. Actually, these photons released at the moment of recombination are what we see today as the relic radiation of the cosmic microwave background. Next, the formation of the first stars occurred. It is assumed that these were very massive stars with a short lifespan that did not survive to our times. The first quasars, galaxies, and galaxy clusters and superclusters were formed. Subsequently, the formation of the interstellar cloud, which gave rise to our solar system, gradually occurred. Around the young sun, a gas-dust cloud formed. It should be noted that this disk was a remnant of the cloud from which the sun itself emerged in its early stages. This cloud gained rotation, which led to the formation of a rotating, flattened disk instead of a spherical one. At the beginning, the disk was 98 to 99% composed of hydrogen and helium, and the remaining elements were present in negligible amounts. However, it is precisely with their presence that the origin of planets is associated today. As the cloud cooled, refractory substances such as iron, silicon, titanium, nickel, their compounds, and others began to condense into dust particles. Condensation means transitioning from a gaseous state to a solid or liquid one. In the planetary cloud, there were no suitable conditions for most substances to exist in a liquid state, so gases heavier than helium and hydrogen immediately formed solid particles, bypassing the liquid phase. An example of this behavior can be seen with water vapor on Mars. Due to the relatively large mass of dust particles, they tended to gain more stable movement, moving toward the center of the disk. Gradually, a thin dusty disk formed inside the thick gas-dust cloud. With cooling, the number and size of dust particles increased, and the density of the dust disk increased. The rest of the initial disk became increasingly sparse. Eventually, the dust disk became many times thinner than its diameter. The composition of this dust disk was different in its different parts and depended on the distance from the sun. The inner regions, heated by the central star, cooled down, and more substances could form solid particles. For example, water vapor could transition into ice, probably somewhere around Jupiter's orbit and further away from the sun. At the same time, the solar wind blew lightweight gas molecules from the inner parts of the solar system faster than from the outer parts. As a result, gas almost left the regions close to the sun. The gradual cooling of the cloud facilitated the formation of countless compounds, mostly entering growing dust particles. According to the laws of physics, gases were more willing to condense on existing dust grains and less eager to form new ones. By the time the formation of the thin dust disk was completed, its density was tens of times higher than the surrounding gas density. The sizes of solid particles reached several centimeters, and the disk became gravitationally unstable. Random compressions in the disk did not dissipate, but on the contrary, kept recurring. This process culminated in the formation of millions of bodies several kilometers in size, which became the embryos of planets. They were named planetesimals. The composition of these planetesimals varied according to temperature conditions and the initial disk density, which, as we mentioned, depended on the distance from the sun. During the next several hundred million years, the largest planetesimals grew, accompanied by the destruction of smaller ones. The small planetesimals were also ejected from the solar system due to the gravitational influence of the massive planets. The fastest growth was observed for Jupiter, as it was situated in an area where icy water particles had already formed. These icy particles contributed to Jupiter's rapid initial growth. Another important factor that gave Jupiter an advantage over other giant planets was its closer proximity to the Sun, where the dust disk's density was higher. The embryos of Saturn, Uranus, and Neptune lagged in growth compared to Jupiter due to the lower density of the disk in their formation regions. Jupiter managed to accrete a vast amount of gas while it was not yet swept away by the solar wind. Today, we see that Jupiter is the most massive planet among all the others combined in the terrestrial group. Though they formed in the densest regions close to the Sun, they couldn't become the most massive planets in the solar system due to high temperatures and dense solar wind streams. Solid particles formed with less enthusiasm, and heavy substances like iron and silicon were in the minority in the initial cloud. As a result, the solar system got small planets near the Sun, mainly consisting of silicon, iron, and their compounds. Among these planets, only Venus and Earth have sufficient mass to retain an atmosphere, which consists primarily of heavy gas molecules that move less rapidly. Therefore, the Moon and Mercury have almost no gaseous envelope, and Mars has already lost almost all of its atmosphere. During the formation of planets, smaller particles collided with each other. If such a collision occurred near a future planet, the colliding bodies could lose so much velocity that their orbit around the Sun became impossible. They were influenced by the massive planet's gravitational pull and became involved in its rotation. This way, rotating swarms of particles formed around large planets, a fate resembling that of the dusty disk. Soon, satellites began to rotate around planets, following the galaxy's perception of time. Another hypothesis states that planets were never molten spheres. According to this view, they originated from the gas and dust nebula surrounding the Sun, gradually condensing into a gas-dust disk, which eventually fragmented into separate parts. Some of these condensations grew to the size of planets. For example, our Earth formed from its embryo in approximately 100 million years. During that time, enormous meteorites falling on it heated its depths and left numerous craters on its surface. Later, the air and water erased most of the craters on Earth's surface. However, on other celestial bodies where these essential components didn't arise, such as Mercury or Mars, the craters remained intact. Moreover, the study of planets beyond our solar system revealed discrepancies that raised doubts about the hot disk hypothesis. Some of these inconsistencies were related to the class of planets known as hot Jupiters, which have orbits close to their stars with periods of a few days. Astronomers made adjustments to the hypothesis to address these questions, but it didn't solve all the problems. Thus, for now, we have to be content with theories that, while not complete, can partly explain the origin of everything related to the surrounding space. Perhaps a new physics will offer the world of scientists who can explain ancient processes in a new light.